Dr. Ma is a plasma physicist at Livermore. She earned her bachelor's degree in aerospace engineering from Caltech in 2005 and received her master's degree in 2008 and PhD in 2010, both from the University of California, San Diego. Dr. Ma always knew that Livermore was one of the most exciting places to be, and she wanted to work with the biggest, most energetic in the world to push the frontiers of fusion research. Following graduate school, she completed a postdoc at Livermore before becoming a staff scientist in 2012. She was awarded the Presidential Early Career Award for Science and Engineering, the highest honor bestowed by the United States government on early career science and engineering professionals. She also received the American Physical Society 2016 Thomas H. Stix Award for outstanding early career contributions to plasma physics research, and she has been named a 2018 recipient of a prestigious early career research program award from the Department of Energy's Office of Science. Her talk today will be recorded, so if you do not want to be part of that record, please log off. This talk is with all our colleagues, including non-Livermore employees, so please keep all conversations unclassified and non-export controlled. Please enter your questions in the chat field and I will read them at the end. Thank you again for being here, and please take it away, Tammy.
Thank you, Paul, and thank you to the HEDS Center for the invitation to give this talk. I'm really excited to be able to share with many of you our future perspectives for high-intensity laser HED science, both in addressing NNSA challenges and how we are currently engaging the external community. I come at this from two relatively new roles that I stepped into about a year and a half ago. The first is as an associate program leader for HEDLP within PLS, within physics, where I am the conduit between the lab and HEDLP funded projects within the Fusion Energy Sciences program at the Office of Science. My other role is as the program element lead for high intensity laser HED science within advanced photon technologies, APT. And for those of you familiar with the lab and its structure, this is the program that was led by Konstantin Hefter before he left to take a position at the Fraunhofer Institute. But what we actually did was we took APT and actually split it to have both a laser development side and then a high intensity laser science side. And the idea is to bridge the science and laser development closer together. And this program sits within NIF. Okay, so first of all, I would like to acknowledge just a huge number of people that have contributed to this work and to the vision. This includes the names here, the NIF and ARC facility staff, and also many external collaborators. And we are constantly adding more to this list. Even compared to just a few weeks ago, there's actually a lot more names that should be on here. Okay, so the outline of the talk is that there are currently many challenges facing our science-based stockpile stewardship program over the next decade. And some of these will require innovative and advanced HED capabilities. So the multi-pronged approach that we are taking in APT to help contribute to solving some of these challenges is by utilizing, first of all, utilizing our current state-of-the-art laser facilities, including NIF-ARC, to develop advanced laser-driven sources. And then we're looking at developing next-generation capabilities. And I'll spend quite a bit of time on this, talking about both high rep rate and how we're bringing cognitive simulation into our HED work. And then enabling future capabilities for DOE through innovative photonics technologies, and finally, partnerships and external engagement. So our goal here is really to bring world-class high-intensity laser HED physics to both make frontier scientific breakthroughs and strengthen the nation's security. WCI recently put out a draft strategic plan. If you haven't been able to get your hands on it yet, the WCI senior management is working on putting out a final draft, and I'm sure it'll be out soon. But there were many people across the lab that actually contributed to kind of laying out a vision, a 10-year vision out through 2030. And as documented in this plan, our SSP enterprise does face several major challenges, and I list just two of them here. The first is the need to make impactful assessments utilizing HED capabilities on an ever faster timescale. So currently, issues that pop up as we do our LEP work, as we do other help solve other problems for the weapons complex, it routinely takes us 3, 4, 5, 6 years to find technical solutions and answers to those problems. We need to speed that up. And then another challenge is this evolving competitive landscape as more institutions and more countries aggressively engage in the field of HED science. So to address these challenges over the next decade, the plan is to, firstly, closely couple HED activities with those anticipated needs. And with that, have an associated suite of experimental platforms, experienced staff, so that we can answer those stockpile questions within 1 year, something on the order of 1 year. And then to address that evolving competitive landscape, we want to develop a purposeful set of partnerships and engagements to better leverage both national and international HED efforts. I think in the past decade or two, we at Livermore and our colleagues at some of the other national labs, we've done such a great job of turning HED science into its own field. And many of our fellow nations outside of the U.S. Have really seen the potential and are interested. So things are going, both in fundamental science and more weapons-based science. And so it is definitely to our benefit to not just see them as competitors, but also to leverage the work that they're doing as well to supplement what we're doing. Okay, so let me first start by talking about how we're using the NIF-ARC to develop some of those advanced laser-driven sources. As many of you probably already know, probably better than me, our stockpile missions do require high-energy X-ray backlighters. And we're talking about energies greater than, say, 20 keV or so. And a couple of the examples for why are shown here. We want to look at implosion hydro of complex systems, high Z material strength at high pressure, and probe, for example, the shape of the compressed cold fuel in our ICF implosions, something that we're still partially quite blind to. And so to do these, we need very high energy X-ray backlighters that can probe these very dense, high Z conditions that are rapidly evolving. Now, how come on NIF we can't just divert a couple of those 192 long pulse beams to generate that X-ray backlighter for us? Well, it turns out that the laser to X-ray conversion efficiency for long pulses like NIF, which are nanosecond type beams, is actually very low in this high energy X-ray range. So instead, we can use laser plasma interactions from short, and by short I mean picosecond, so 1,000 times shorter ultra intense lasers to generate those bright X-ray and particle sources that we can then serve as probes and backlighters. So a super quick, super dirty overview of what an ultra intense laser matter interaction looks like is shown here. You bring in your intense laser, and by intense we're talking about intensity greater than 10 to the 18 or higher. It hits a solid target. The laser is relativistic, and so you get to actually wiggle the electrons within the plasma that you generate directly, generating a relativistic electron beam. Those electrons stream through your solid target. You generate Bremsstrahlung photons, and then as those electrons stream out the rear surface, you can also get beams of X-rays, positrons, protons, and heavier ions, what we call secondary particles that are accelerated as well. So by adding this higher radiance, high energy short pulse laser on NIF, we have an additional unique and significantly enhanced capability to perform some of those critical experiments that we need to do. And all of you know that that laser is what we call ARC. It uses 2 beams from a single NIF quad to amplify 4 short pulse beamlets. So we like to say that ARC is a laser within a laser. Very quickly, it contains a high contrast front end. It does use the NIF amplifiers, but going into its own final compressor. And then focuses that compressed high energy laser down using off-axis parabolas. So there are 4 beams at 1 omega, so 1 micron wavelengths. And now because the final focusing parabola has to sit outside the NIF chamber, which is 10 meters in diameter, so we're limited in the F number that we can actually get, or actually have, right? So it's a 40 by F40 by F60, giving us a relatively large focal spot for these intense lasers. And so we're actually limited in the peak intensity that we can actually achieve with ARC. And so in this table on the bottom left are some of the beam parameters. We can get up to a kilojoule per beamlet for a total 4 kilojoules at 30 picoseconds. And our peak intensities are just brushing 10 to the 18th. So we're just barely relativistic. So, you know, ARC is a great tool, absolutely. It has very high energy, but because of its large spot size, we are limited in the overall intensity we can get to. There has been quite a lot of work going on to look at novel ways of increasing the ARC intensity. And this work has been through actually a number of LDRDs and currently is being covered under Andy McKinnon's SI, where they're looking at compound parabolic concentrators, CPC targets. And the idea of these conish-like targets is that the ray of every single, every light ray coming into the CPC gets focused to the cone tip. And so it's very advantageous for something like an ARC spot, which is very large. An example is shown there on the left. You get 50% of the energy in 130 micron diameter, and you have to go out to 550 microns to capture 95% of the energy. However, if you can dump that into a CPC, that can all get focused to a much smaller output. And then just to give you an idea of what that kind of target actually looks like, it's shown there on the bottom right with its actual scale. And I'll direct you to a great Optica paper written by Andrew McPhee that was published. Oh, I think that's a typo. I think that, oh no, that was last year, 2020. Excuse me. Yeah. And shooting into these CPC targets has actually shown enhancements already of up to 4x in hot electron temperature, which corresponds with 16 times in X-ray yield versus a flat target. So on the right there, you see a series of shots that were taken on the NIF ARC with those 4 beamlets. 4 beams on a flat target, 4 beams into 4 CPCs, all 4 beams into a single CPC, and you can see the corresponding enhancement in electron temperature and yield. And simulations do indicate that the boost comes from both geometric focusing and a advantageous plasma confinement that you have. The CPC shape helps to hold in an underdense plasma from the laser early in time as it comes in. And that plasma later on helps to improve both the coupling of laser energy into the target and also gives the hot electrons more room to accelerate up in energy as well. This work, if you're interested, there was a very nice series of APS talks this year from Sean Kerr, Dean Rusby, Nuno Lemos, Ginny Cochran, Andreas Kemp, and some papers that should be coming out on this. And Jackson Williams as well, coming out on this soon. And then to give you an idea of the improvement in radiographic capability that we get with these enhanced X-ray yields, we show you a couple of radiographs of a target with 3 shots on ARC. And basically, this increased X-ray brightness does provide us with the increased utility that we need, i.e. radiograph signal to noise ratio for those NNSA missions. And just by adding the CPC target, essentially we have an improvement in laser intensity of an order of magnitude. So it was a very cool science result, but also for us a very cheap way of actually increasing arc intensity without having to do upgrades to the laser itself. So a great outcome. Now, besides X-rays, we've also demonstrated a robust proton source on the NIF ARC. And for those of you familiar with target normal sheath acceleration, so this is the scheme where you generate electrons, hot electrons, when your laser comes in. As the electrons escape out the rear surface, you set up this sheath field, electrostatic sheath field, that pulls protons off the rear surface of your solid target, giving you this beam of protons. With TNSA, there's been a large body of work done over the past 2 decades on short pulse facilities around the world. And most of those facilities have lasers that are less than a picosecond in pulse duration. And one thing that most TNSA experiments have been focused on is measuring the peak proton energy that gets accelerated. If you plot out peak energy versus laser intensity, they constitute all those blue points that you see in that plot on the right. And they typically tend to follow a decent scaling with laser intensity of I lambda squared. And you can see that there's a pretty strong scaling. But we knew before we shot on ARC that we were going to be battling with low intensities, around 10 to 18. And so there was some worry that we might not be able to generate protons. However, when we took our first shot, we found out that max energy on ARC exceeded this conventional scaling by 5x, which is just wonderful. And this is in large part due to something called superponderomotive electron acceleration. The long pulse lengths of ARC actually work in our favor because what happens is the early part of the pulse comes in and interacts with your solid target. You generate an underdense scale length that actually helps for the acceleration of these protons as the subsequent portion of the laser comes in and generates electrons. And also, you get to set up these quasi-static magnetic fields that also help to accelerate electrons to higher energies. And the higher electron energy you have, the higher proton energy you can then have as you pull off protons from the rear surface. Without having a lot of shots on ARC, of course, we haven't been able to do complete optimization yet. But we've already found a maximum energy of over 30 MeV, and this is interesting because these protons are now energetic enough that we can do deflectometry in hole ROMs and actually probe the magnetic fields inside those hole ROMs. So this is work that John Moody and Brad Pollock are already starting on. And also super exciting, we demonstrated a decently high conversion efficiency. So we got over 50 joules into protons when we shot ARC at the 10 picosecond pulse length. And I'll just note that 50 joules of protons is more energy than most laser systems themselves around the world. A number of good papers coming out, Darius Mariscal, Raspberry Simpson, shown there on the right. And so this new physics of proton acceleration can be explored on ARC while we develop applications such as proton focusing, isochoric heating, and also proton radiography. The other super great thing about ARC is that it's reliable and it's well characterized. So we actually know exactly what the laser actually delivers. For those of you familiar with the field of short pulse, this is actually pretty revolutionary to know what the laser is spitting out for us. And so using this high fidelity on-shot laser characterization, we can actually feed that into our modeling. And now we have a characterized input basically giving us a predictive capability that we can believe and that we can directly validate. And so over the past few years, we were able to put together this modeling framework led by Scott Wilkes, Andreas Kemp, Juwon Kim from UCSD, where we actually had to combine a number of different techniques and codes. So first of all, Scott would run Hydra to generate the pre-plasma conditions from the pre-pulse of the laser. He would hand that off to Andreas to do 1D PSC PIC modeling to give us what the electron acceleration looks like, and that got handed off to Juwon to do LSP modeling to give us subsequent, for example, in this case, proton expansion. And the idea is we have to encompass such large temporal and spatial scales that we needed to combine a number of the different tools available. And this is a true predictive capability. Before we shot our first proton shot on ARC, this team went and told us that we would be getting very high energy protons, and we didn't actually believe them. But when we went and did our first shot, we found that indeed the proton energies were 5x what you might expect from that conventional scaling. And so, you know, in NNSA terms, of course, the predictive capability is always something we want to improve. And in particular, that laser plasma interaction is something that is really, excuse me, really important for us to capture correctly in our codes. So moving forward, using this new predictive capability and novel techniques in pulse shaping, and here again, we get to pull in cool new work from NIST. So this is a team by John Huebner, Daniel Mittelberger, Ryan Meir. They've developed new techniques to actually pulse shape short pulse lasers similar to what we do on NIST with resolutions below a picosecond, hundreds of femtoseconds. And so on the left is an example of what a shaped short pulse might look like. I know it looks a lot like a NIST pulse, but instead of nanoseconds, it is in picoseconds. Our simulations applied to these types of pulse shapes tell us that we can extend the max proton energies quite significantly compared to the conventional pure Gaussian laser pulse that you might have for a typical short pulse laser. And so again, a wealth of physics that we can look into here about time-dependent laser plasma interactions, time-dependent particle acceleration, because really we get to delve into the laser absorption directly. So this work is being led by Derek Mariscal under an LDRD funded by NIF. So NIF is putting in a bunch of good institutional investment into this idea. And then once we figure out how we can tailor particle sources, that means that whatever application we need, we know how to provide the particle beams to feed that application directly. Another secondary source that we are interested in is laser-driven neutron beams. These neutron beams will also enable innovative diagnostics and new approaches for our stockpile missions. So a typical scheme for how to generate those neutrons with short pulses is shown there on the left, what we call a pitcher-catcher type geometry. You have your primary target where you generate a beam of protons or heavier ions like deuterons. You slam them into a secondary target, which could be lithium, beryllium, whatever, to generate your beam of neutrons. And the idea is there's a lot of potential advantages over conventional accelerators that generate neutrons. For example, we can get ultra-short pulse durations, basically on the order of the laser beam and the interaction itself. So, less than a nanosecond for sure. Very small source size. Your beams can be directional. If we can figure out how to tailor our sources, we'll have spectral selection, very high peak brilliance, etc. And another nice thing is you could have as many frames as you need for your radiography. It's just limited by how often you can shoot the laser itself. And the idea with why we're so interested in neutrons is because they are highly penetrating and discriminating. In that first picture on the bottom left is a neutron radiograph of a rose inside a lead canister. Neutrons are material selective. They directly probe the nucleus, and so you can differentiate high Z materials from low Z materials, but also by the number of what your nucleus actually is, and then activate fissionable material as well. So lots of advantages there. And so we are currently working with subject matter experts across the lab to identify those potential high impact applications, and then derive from those applications what the requirements would be for a laser-driven neutron source before we go off and actually do a lot of the experimentation. This will set the requirements for us. And so this is a feasibility study, LDRD, led by Jackson Williams, going on right now. And Jackson is going around the lab showing this plot from on the right, showing how a current laser-driven neutron source looks like, and how potential future ones might be able to deliver as well. And then talking to our SMEs about pros and cons and potential applications, and working with Maury Osterheide to do simulations as well. And so short pulse laser-driven neutrons do have the potential to be a compact, versatile, high brilliance source for NNSA and civil applications. I would be. Yes, Paul.
Just one note. So your slides are marked official use only. Is that an old marking?
It is. No, it's fine. It's fine to be shown here. It's gone through IM and everything is unclassified. It's official use only because it is our kind of strategic plan going forward. But it's fine for open circulation.
Okay, so just to be clear, there are not a lot of people here on this call.
Yeah, no, that's okay. That's okay. A good portion of these slides were used in the NIF ERC a few weeks ago, so they have been shown to the public. Yeah, sorry about that. And we're also developing a stagnating neutron source platform on the NIF, and this is again under Andy McKinnon's SI, work by Matthias Hohenberger and Nathan Neeson, looking at a single-sided inverted corona target. So basically a exploding pusher that we are driving with just a subset of NIF beams, so that you have the remainder NIF beams to drive whatever other target shock experiment you want to do. This platform has already shown DD neutron yields of low 10 to the 12th, which is equivalent to 10 to the 13 neutrons per steradian using a DT fuel. So this is another potential relatively high neutron yield source that can be used for our experiments. And there are more experiments planned on Omega and NIF this FY coming up. So high-intensity laser-driven photon and particle beams will enable a myriad of exciting applications, and I list just some of them here. proton radiography and deflectometry, building off of work that was done in the very early years on NOVA and JLF, high X-ray radiography of high ROR objects. We could potentially use these particles for isochoric heating to generate warm dense matter as well. These proton beams are not only directed, but due to their properties, can very precisely deposit their energy very quickly. So it is a way of actually heating up our samples by depositing a beam of protons before that sample has time to hydrodynamically expand, so what we call isochoric heating. And this is a way of getting us to HED conditions that are otherwise quite difficult to precisely reach. Nuclear reactions in plasmas, stopping power investigations, and then, of course, preheat and equation of state studies as well. So a bright future here for using these particles for sure. Okay, so let's move on to the next section, which is about shifting paradigms from shot per hour to shot per second, and developing future capabilities. So again, a major challenge facing our science-based stockpile stewardship enterprise is the need to make those impactful assessments utilizing HED capabilities on an ever faster timescale. And this can be addressed a number of ways. The first is, of course, just developing a range of ready or already demonstrated platforms. But we really like the ability to rapidly develop new platforms for those applications as well. The important thing to keep in mind is that those platforms have to be at weapons conditions or weapons relevant conditions where we understand the scaling. We also want to foster more responsive, higher quality and quantity HED experiments. And then finally, exploit the synergy between design and codes and modeling and experiment. So our goal within our group is to develop a high throughput capability that is demonstrated to rapidly respond to some of those stockpile questions. All of you know that are very familiar with these premier facilities that I show on this plot, facilities all around the US and the world to conduct that forefront HED science that we do. But until recently, we've been using these large energetic drivers that are mostly single shot, meaning you get a shot, if you're lucky, shot per hour. NIF is shot every 4 or 8 hours or more. But the cool thing is the next generation lasers coming online are already rep rated, greater than 10 hertz, so 10 shots per second. We really need to figure out how to exploit this capability. And so some of those rep rate capable laser facilities are shown here. The HAPLS laser was the one that was built by APT under Constantine and shipped over to the Czech Republic for the Eli beam lines. That is a petawatt class laser at 10 hertz. Sorry, not even petawatt class, petawatt laser at 10 hertz. But the other side of APT, led by Tom Sminka, is already developing more advanced laser architectures, such as the Shark laser there in the middle, which uses the HAPLS front end, but direct CPA, and then even a BAT system, which uses new novel gain media, like thulium YILF, which allows for multi-pulse extraction, giving you kilohertz or even 10 kilohertz rep rate levels. So the takeaway here is that the US actually leads in laser technology development. We need to maintain this. By pursuing new and very innovative laser technologies, this will enable additional science opportunities. And really, high rep rate laser science represents a very radical paradigm shift in the way we do these HED experiments, because high rep rate not just means more shots and therefore more data, it also means more statistics, and once you have that, more precision, you can bring your error bars down. You can explore more phase space and essentially do more experiments to give us that faster response we need to close those mission need gaps. To further convince you, many HED experiments will benefit from this. For example, in the realm of high-pressure material properties, this is a plot taken out of the McWilliams science paper looking at phase transitions in magnesium oxide. If we have what he shows here, he got this science paper out of 2 shots. But if you have more shots, you have more measurements, and you can access a larger phase space and really map this full plot out. In the realm of opacities and radiative properties, Jim Bailey at Sandia has been looking into this discrepancy between the codes and what he—
Sam has been modeling.
I don't know if that was a comment for me. Anyways, this discrepancy between codes and opacities, and Bob Heater has been trying to verify on this whether what Jim measured was correct or not. But really, this is something where we could really increase the measurement confidence through high statistics to constrain those complex models that we use for stockpile assessments. Of course, secondary sources, I already talked about this quite a bit. With ref rate, you can have high brightness, you can tune your beams are reproducible for those needs of probing, heating, radiography, and then finally, plasma nuclear physics. By having high average numbers of particles, you can start to probe some very subtle and rare nuclear reactions. Okay, so what do I actually mean when I say high rep rate? Let me walk you through what we're envisioning. This is a typical laser plasma experiment. It'll look very familiar to all of you. You have your laser, you shoot a target, you generate your HED plasma, you diagnose it with a variety of diagnostics, and then you do some data analysis. You churn on that data analysis, or maybe your grad student does, and then you decide, okay, what do I want to do for my next shot, right? And you give instructions to your laser, build your next target. However, in a rep rate paradigm, you have your laser running at 1 hertz, 10 hertz, very fast, right? We can't just rely on humans to evaluate whether or not the laser is giving us what we said we wanted and whether it's safe. So you have to develop this laser control system where your laser system diagnostics feed back in and ensure that your laser is staying in a safe operating regime. And this feedback loop we call just the laser loop. Now, if you're running at rep rate, it also means you have to feed in targets at an equivalent rate. We need high rep rate targetry. And then your diagnostics will be reading out that data at that same rate that your experiment's going. So now you need data handling and processing as well. You can start adding in operational feedback as you're taking your data. You want to make sure that the data is optimal and whether or not your diagnostic might need to change filtration, gain settings to give you good data. And furthermore, you can maybe even clean up your data in real time such that what's coming out is what us as physicists are looking for, right? You can clean up the noise, clean up the background, spit out some analysis, some analyzed values, right? And in a rep rate regime, you really can start to leverage integrated analysis, where you're pulling in the data from all of these disparate, different modes of data to give you a better understanding, and you can start looking at trends across all of these different diagnostics simultaneously. Now, for true integrated analysis, of course, you want to feed in what the laser's doing, feed in what your targets are, and then feed that into an optimizer so that you can decide what to do on your next shot. And then propose those inputs to your laser and to your target system as well. And this is what we're calling the experimental loop. Now, where rep rate really starts to be a super leap forward is when we start to fold in our HED codes. We can use these HED codes to help us understand our integrated analysis, and furthermore, use our data in real time to improve our HED codes, improve the physics in our HED codes, and feed that also into our optimizer to improve our experiment. So this is our modeling and simulation loop. So for us, this high rep rate laser science means a fully integrated system that leverages technological capabilities in many domains. And it's not going to be easy. There's obviously many challenges, but we are starting to address them already. And the really awesome thing, and what makes me so proud to actually work at Livermore, is that we are really the only place in the world right now that has such a unique and strong infrastructure of capabilities, competencies, that we can really pull together to expand our knowledge of plasma physics. And some of those competencies are listed here. Optical technology, we are still very much the leaders in fabricating large laser optics. We have some of the premier HPC tools and HD codes. In terms of target fabrication, we can do very exquisite, complex targets, but we are also innovating with.
I think what we talked about is doing either 35 or 36 stages and
additive manufacturing. And we're talking to Chris Fettuccini now about developing novel targets and also adaptive preparation, building new targets at similar rep rate to give us unique targets every time we want to shoot at these 1 Hz, 10 Hz rates. We get to leverage our current knowledge in terms of running big laser facilities, community ties, diagnostics, et cetera. So we're bringing all of this together to complement and enhance our high throughput HED experiments. But one of the major bottlenecks right now is still the lack of appropriate diagnostics. And so we just started a new LDRD this year, led by Graham Scott, where what we're doing is developing a suite of diagnostics that are rep rate capable, and that are also robust to HED environments. So now that you're running at rep rate, you're also generating a lot more debris, a lot more high energy radiation, EMP, that if you really truly want to run at 10 Hertz, your diagnostics need to be able to withstand. So that work is going on by looking at novel detector schemes, scintillator development, et cetera. And then also developing high throughput analysis. So at a 10 Hertz shot rate, you get a huge ton of data coming out. And we absolutely need to develop machine learning based algorithms for real-time analysis of these experiments. And finally, then develop the active feedback, taking the experimental data and looping it back into the laser system. And then with that, Graham will be applying a science question to this, which is how you can optimize secondary source. For example, how can you boost the proton energy even higher, or the flux of protons even higher? Now, coupled to that, we were awarded a FES award this year, Fusion Energy Sciences, from the Office of Science, so external money, to take these rep rate diagnostics and deploy them at Colorado State University. They're a left laser, which is capable of 3.3 Hertz. And this would be a blueprint for scaling these capabilities to other LaserNet US facilities across the US, which is a network of 10 mid-scale lasers, similar to Titan at JLF, and really make this a capability that is available to US researchers. Separate from that, FES also recently awarded us $3.8 million over the next 3 years to develop cognitive simulation as applied to these HED laser experiments. So there was a report that came out last year. I encourage you to look at it. It's really quite informative. Actually, just look at the summary brochure, which is 2 pages instead of the full report. But this was a workshop on advancing fusion with machine learning. And the idea was to really couple experimental data and simulation data closer together to inform both your experimental design and your physics understanding. And this is all just possible now because of the simultaneous revolution in computational power and machine learning techniques, and in our case, high rep rate lasers. And so this is a really cool project that has multiple thrusts, which I don't have time to go into. But some of the things that we're interested in doing is multimodal representations. For example, your data comes out in all different forms, right? You have your electron spectrometer, which is integrated spectra. You have 2D images, you have street camera data, and you want to use this multimodal data and couple that to multimodal modeling to capture and model the correlations between this rich set of data signatures. We're also doing a variety of transfer learning, virtual diagnostics, for the first time applying UQ to short pulse experiments, and then really also doing advanced architectures. So essentially edge computing, putting some of that computational hardware directly in our diagnostics, but also figuring out what that hardware system looks like that you might want to actually put right next to your laser, rather than, you know, up in the cloud or some big server somewhere else, because we need to start thinking about latency times and how quickly we can send data back and forth when you start ramping up your rep rates. And so here we're combining cutting-edge machine learning with operations to demonstrate real-time feedback. You know, not just feedback into doing better experiments, but on the fly, improving our models as well by incorporating live experimental data. Then another thrust here is plasma optics. And so this is research led by Patrick Poole, Bob Kirkwood, Pierre Michel, Andrew Longman, their teams, to really look at how we can manipulate plasmas to generate this next generation capabilities, such as dispersive plasma gratings or plasma amplification of very short pulses. In a disruptive research LBRD project that Patrick's leading, they actually demonstrated a plasma amplifier on NIF by combining a number of beams. And I believe that paper is on its way. Oh, no, that paper did come out, actually. And so the idea with plasma optics is you can allow for smaller scale systems. We can potentially push beyond the limitation in laser intensities that are currently limited by hardware and damage the systems. They're also very compatible with tailoring light at rep rate speeds. And we see this as a generational leap, similar to what chirped pulse amplification did for lasers in general. Okay, and then finally, I'll shift gears to quickly talking about developing a purposeful set of partnerships and engagements. This map here on the bottom is actually taken out of the NAS study from 2017, showing the concentration of laser power around the world. And you can see most of it is actually outside of the US right now. It resides in Europe and it resides in Asia. So here in the US, we have to do something to make sure that we stay competitive and maintain our leadership. So one of our projects right now is that we are strongly engaged in the SLAC Matter at Extreme Conditions MEC Petawatt Upgrade Project. This is a project that is funded by, again, the Office of Science. And the idea is that they would put in a new experimental cavern beyond the current STAR experimental hall, for those of you familiar with MEC. So this is something beyond where the current MEC is. They would put in a 150 joule, 150 femto, 10 hertz, 1 petawatt laser. And currently, Livermore is slated to build that. Couple that to a kilojoule, 20 ns shaped pulse. That would be a shot every 30 minutes long pulse laser for shock compression. And LLE will probably be building that. And together, these lasers will be coupled to the newly upgraded 24 keV XFEL beam. So you can imagine, just by combining all these forefront capabilities, how cool a tool this will be for some of the HED science we want to do. So it is a $200 million Office of Science project. CD0 mission need was achieved in January of last year, and they are aiming for CD1 in spring. of this year, and if everything moves smoothly, the expected completion date is 2026. And I'll take this opportunity to thank many of you for being involved in actually helping to define the key HED experiments that we want to do to set those requirements for facility configuration. And I'll just note that we're actually continuing to explore with NNSA participation in actually sponsoring multiple kilojoule long pulse speeds. So adding to that 1 kilojoule to make it a 5 kilojoule multi-beam long pulses that would get added so that we can get into even higher density regimes relevant to what we care about here at Livermore and across the NNSA complex. Truly, this is something we've been talking about for years and years. We're very fortunate here in the Bay Area. And it would be great if we could turn the Bay Area into an HED powerhouse. And one of the ways is by building up a partnership between Livermore, SLAC, and LBL. And this is one of the slides that we try to show our management to get them on board, that we already have a robust collaboration between Livermore and SLAC physicists. About 40% of the papers coming out of MEC to date have already involved Livermore co-authors. And so we are working to continue to strengthen this partnership and our partnership with LBL as well. Livermore is also a strong supporter of LaserNet US. This was a program started in 2018 by the Office of Science, pulling together 10 mid-scale laser facilities across the US and Canada. And Livermore has been quite instrumental in its success so far. So JLF, Jupiter Laser Facility, is part of LaserNet, providing time on Comet and Titan. Felicie Albert is this year's chair of LaserNet US, and I myself actually established and continue to run the proposal review panel for LaserNet, although hopefully I'll get to step down from that soon. Quite a few of our scientists serve on this PRP panel, and many scientists of our scientists apply for and participate in multiple LaserNet US experiments each cycle. And we also actually help LaserNet administer user funds to allow other people to travel and obtain new equipment. Livermore will also be leading the first US experiment at the Eli beamlines on the HAPLS laser in the Czech Republic. And this was under the new Department of Energy Czech Academy of Sciences cooperative agreement that was signed in 2019. And so, it was, for many of us, it was really painful when HAPLS got built, but then got shipped overseas. But we can actually still use this to our advantage. We can go over there, do experiments, and the expertise that we will develop in performing those experiments will actually inform and support the development of the next generation, the next high-intensity capability in the US. Almost there. Our HED physicists have also led and participated in a number of community initiatives over the past few years, advocating very strongly for increased investment in high-intensity laser science. Some of those reports that came out are shown here: the Brightest Light Initiative, the NAS Plasma Decadal Study, and the report that was just released last month, which was a long-range strategic plan for fusion energy sciences. And I will just comment that the CSAT plan does advocate for construction of several new high-intensity, high-power laser facilities, and very exciting for us, the reestablishment of an inertial fusion energy program in the US. And as of the omnibus that was signed right before the new year, the Energy Act, as part of that omnibus, actually stipulated that the Office of Science does need to restart this program. And so you'll see that coming on the horizon soon. So very exciting. So I'll just wrap up that advancing HED capabilities is crucial to addressing those stockpile stewardship challenges, which do include making impactful assessments, utilizing HED capabilities on an ever faster timescale, and maintaining leadership amidst this evolving competitive landscape. We are enabling future capabilities for DOE through innovative photonics technologies and applications. This includes using the forefront tools that we have already, as well as developing new ones and moving to next generation capabilities such as RepRate. And so it is crucial for us to maintain U.S. leadership and prevent technological surprise in the photonics technologies and applications. And one of the ways we're doing that is by developing this very purposeful set of partnerships and engagements. And so our work, we hope, supports the SSP mission, also bolsters the reputation of Livermore by getting our scientists and our science out there, while opening entirely new programmatic and scientific space in HED and lasers. Thank you.
Thank you very much, Tammy. That was a very nice talk. So please enter your questions in the chat field. And in the meantime, please also unmute yourselves so we can all give Tammy our thanks. So I thought that Ray Aiea had an interesting observation that through much of your talk there, we got 192 participants. Of course, very auspicious number for all us NIF fans. Sorry?
I said my favorite number.
Yeah. So Bruce Remington asked, is the 30 MeV target normal sheath acceleration proton result published yet, which Scott Wilkes was nice enough to answer in the chat and gave a link to older 18 MeV work.
Yeah, Bruce, I'll just say that the 30 MeV, we know we actually got a lot higher energy, but because it was NIF, we were limited in diagnostic flexibility, and we actually just ran out of room to put more pieces of RCF in the diagnostic. I think Derek and Graham have worked on a new design where we can get to much higher energies, and we'll see. There's Derek's shot day is in April, I think.
Cool. And actually, asked, is the optimal pulse shape for short pulse to maximize the proton energy known, or is this still being explored? There's also a related comment from Derek Mariscal saying that the short answer is that it is still being explored both in simulation experiments, but the picket and pump configuration that Tammy showed is promising, at least for multi-picosecond systems like ARC. We are starting to explore more thoroughly using ensembles of PIC simulations. The Georgievic due to the large amount of possibilities with pulse shaping. Would you like to comment further, Tammy?
Yeah, I'll comment that this particular problem matches very well with high rep rate because the parameter space, the potential pulse shape that you can explore is just enormous. And so it really fits well with machine learning to try to tackle that space and try to figure out what the most interesting places are to actually explore. But also using some of those advanced AI techniques that I talked about to really better understand the physics of what's going on. For example, with TNSA experiments, we've never been able to directly measure what the electron spectrum looks like inside the solid target or what the sheath looks like on the rear surface. All we can measure are the particles coming out. But if we bring in the power of machine learning, what we can actually do is develop these higher models that fold in all of our diagnostic data, what the inputs are, and then really get a better picture of what's going on in those places where we can't directly measure right now. So that will, to help answer Eric's second question farther down, it will help us to understand the physics a lot better what's going on in the target. We're also improving the resolution of all our measurements and improving our direct measurements of what the laser is delivering us. And with that, we should be able to get a better physical picture of the interaction, laser matter interactions on a time resolved scale that we haven't been able to do before.
Great. Are there any other questions?
Yeah, I had just a quick one. What's the, it seems like, there is a bit more interest now, at least, in developing new facilities and sort of trying to regain that momentum sort of on the US side. Is there any interest from sort of broader government? I mean, I know in the UK, the sort of the Ministry of Defence has taken a bit more interest in source development now on lasers. Is there any engagement on the DoD side on this this area of research?
There's been interest in terms of conversation so far. I can't say that there's anything organized quite yet. But I will say we are planning, I think I saw Sean Reagan on this call. Sean and I are planning to potentially put together a workshop to look at future light sources from these advanced lasers. And so we would love for everybody here to participate as well. And hopefully we can build some momentum there to get DoD interested, headquarters interested, et cetera.
Any other questions? If not, let's give Tammy another thank you via applause.